The science of chemistry has disappointed many people. It upset the Emperor of China in the year 59 BC. He had been told that one of his court officials, Louis Xiang, could make gold. A great feast was organized, at the end of which Louis Xiang was to prepare a small quantity of the precious metal. After toiling away with complicated apparatus for several hours, however, all he succeeded in producing was an unpleasant smell. Louis Xiang was executed on the spot. This true story reflects one of the problems which has confronted scientists throughout the ages. The problem being an understanding of what chemistry really is. Chemistry is the science of substances and how they can be changed into different substances. It is the reasons for the changes which occur in these reactions that have confused scientists for so long. During today's lecture demonstration, we shall be looking at some of the reactions of the element chlorine. Right, Bernie, let's start off. The deflagrating spoon. A little heat will be applied. So we have yes. In the reaction which we are observing here, I am combining two elements which are extremely poisonous and dangerous to life of any kind. The two elements which I have combined are sodium metal and chlorine. And the result of the reaction is the compound sodium chloride. Now this reaction is particularly interesting because we have combined two poisons to make a substance that is not only not poisonous, but indeed it is necessary for life. Chlorine is a member of the group of elements which are called the halogens. The halogens are found on the periodic table in this position here. They constitute group 7, and the elements are fluorine, chlorine, bromine, iodine, and astatine. They are called halogens because the word halogen itself means salt maker. It is derived from the Greek words halos, meaning salt, and genes, to be born. Chlorine, then, is a halogen. It is a member of the group of elements which are called salt makers or halogens. I shall now demonstrate the apparatus which is used for the preparation of this gas. We have here a flat-bottomed flask with some concentrated hydrochloric acid in a tap funnel and potassium permanganate in the bottom. And I shall introduce you at the same time to my two laboratory technicians, Grant Hall and Bernie Mangold. And together we shall prepare just 2 gas jars of this gas chlorine. Why just 2? You'll find out in a moment. So Bernie, let's go. There's one for Grant, one for Bernie. Right, put the delivery tube in. Notice the way I'm collecting this gas, incidentally, by downward delivery. Right, you can see the green color spreading. Are we ready now? Next one coming up. And a little more concentrated hydrochloric acid. Give the mixture a stir. And you observe the green color of chlorine gas filling the gas jar, right? Can we take this away now? Now, there are 2 reasons for collecting only 2 gas jars and also doing it by this method. Chlorine is denser than air, therefore it's conveniently collected in this way. But secondly, and more important, is that chlorine is an extremely dangerous gas. It's very poisonous indeed. And therefore, strictly speaking, this experiment should either be done in a fume cupboard, or, if you permit me to show you, we should be wearing this kind of protective clothing, as you see, full gas mask facilities. So the gas is extremely dangerous. We've prepared only 2 gas jars here. We have, as you see though, several other gas jars which will be used for further experiments. Now the first experiment which I wanted to demonstrate is the reaction of chlorine with water. Could I have half a beaker of water, please? One of the reasons why we didn't collect chlorine over water is because it is quite soluble in water. And I shall now show you this solubility by pouring in a small quantity of water into the gas jar, shaking it up, and you will observe that the water will turn slightly green. Now this is due to the fact that chlorine has dissolved in the water to form a solution known as chlorine water. However, in addition to dissolving in the chlorine water, it has also reacted with it slightly. And we can demonstrate the result of this reaction by pouring in some litmus solution, which tells us the difference between acids and alkalis. You will observe, as I remove the lid, it's rather difficult to remove because of the partial vacuum which is formed, that the solution turns pale red, which shows that the solution is an acid. I can demonstrate for you the reaction between litmus and another acid, a conventional acid, dilute sulfuric acid, and you will observe that in this case the indicator turns bright red. Chlorine then not only forms a solution which is acidic in water, but also has powerful bleaching properties. Litmus is a member of a group of organic dyes which are all bleached by chlorine. And indeed, this is one of the main uses of chlorine in the modern world. It's used as a bleaching agent. So we can take these two gas jars away and demonstrate the next experiment. What was that, Bernie?
One with potassium iodide.
Ah, with potassium iodide. Now this is a very interesting colour change. If you allow me to perform it, I'm going to add potassium iodide solution, which you notice is colourless, to a solution to green chlorine in a gas jar. If you observe carefully, you will observe that the potassium iodide turns brown spontaneously as I pour it into the gas jar. Now there's a very good reason for this. A chemical reaction has taken place. And the reaction may be described simply as follows. Chlorine plus potassium iodide makes iodine plus potassium chloride. Excuse the slight cough, I'm getting rather filled with this chlorine gas. And you notice the dense red colour here, which is due to iodine. Incidentally, iodine forms a brown solution, as we can see here, but there are several other compounds which also form a brown solution. So we have one particular way of distinguishing iodine solutions from other brown solutions. And I can demonstrate this by pouring a small portion of this dilute solution into a tool measuring cylinder. Could I have a beaker? Yes, that's okay. I shall now dilute this with a fairly large quantity of water. Could you dilute it for me, Grant? Thanks. I shall dilute this with a large quantity of water in order that the colour may be less dense. Yes, more. Top it right up with water. Plenty of water. We shall pour it into the... That's perfect. We shall pour this now, this dilute iodine solution, into the measuring cylinder, and we shall now pour onto it some trichloromethane. And as you observe the trichloromethane falling through the solution, you will observe that a layer forms on the bottom of the measuring cylinder which has a different colour. I will stir up the solution a few times just to show exactly how the colour is formed. And you will notice that there is separating out on the bottom a dense purple layer, or a dark pink layer as it's appearing to be, of iodine dissolved in trichloromethane. Now iodine is in fact the only element or the only substance which dissolves in water to form a brown solution and trichloromethane to form a pink solution. We have therefore demonstrated a reaction which is unique to iodine, thus showing that iodine was formed in a previous reaction. Incidentally, a little sideline, if you pass me some sodium thiosulfate solution, you observe another interesting reaction of iodine. This too can only occur with iodine. A little sodium thiosulfate solution there into the top. We stir up the mixture a few times and you will notice that the colour of the iodine disappears completely. This is another very useful test for iodine. Right, the next reaction is that between a very dangerous element, white phosphorus. It's very dangerous because white phosphorus catches fire as soon as you expose it to air. Now you might have observed, as I'm holding this bottle, that the phosphorus doesn't appear to be very white. In fact, it seems to be more yellow. Well, it's also known as yellow phosphorus. It's historically been known as either white or yellow. I have here a sample which I must admit looks far more yellow than it is white. Now we shall pour a few small pieces of white phosphorus onto our deflagrating spoon. As I have said, this is an extremely dangerous element because of the extreme inflammability of phosphorus in there. You can possibly observe it beginning to fume already. Now, when I lower it into the gas jar of chlorine, you will observe that within the space of a few seconds, a vigorous reaction will take place and white fumes will be produced. There it is, it's beginning to sparkle already. And there we go, dense white fumes are being produced of the gas phosphorus trichloride. It's burning with a yellow flame. And this is an example of a spontaneous reaction. By spontaneous, we mean that the reaction happens by itself, without any heating. You'd think that the phosphorus has gone out, but if we raise the deflagrating spoon out of the jar, you will observe that the phosphorus is in fact continuing to burn extremely effectively. In oxygen, the white smoke which is formed is phosphorus pentoxide, whereas in chlorine, the white smoke is phosphorus trichloride. Incidentally, any reaction in which one element combines directly with another element to form a compound is called a synthesis. So far then, we have seen the synthesis of sodium chloride by burning sodium in chlorine, and the synthesis of phosphorus trichloride by burning phosphorus in chlorine. Now, the next demonstration is also a synthesis, only slightly more unusual. I have here some sheets of a very, very thin foil, which appear on first inspection to be gold foil, but regrettably we seem to have run out of it. Oh dear, Bernie, you fooled me. This is a booby trap. Too bad. I can't show you that demonstration. It would have been very effective, but Bernie, could you go and have a look, see if we can find some. See if we can find some Dutch metal. We seem to have been given a collection of Dutch metal sheets. However, we shall run on to the next experiment immediately, and I'm sure we can show you something effective.
Reaction with antimony.
Ah, the reaction with antimony. Antimony is a metal which is not very well known in schools. It's not studied at all because of its rarity, and it's not really used very often. However, antimony has been very well known to people for more than 5,000 years. In fact, it's well known that antimony was used in the preparation of eyeshadow by Egyptian ladies some 5,000 years ago. Not only that, but antimony compounds were used by the famous medieval doctor or iatrochemist Philippus Theophrastus Aureolus Bombastus von Hockenheim, otherwise known as Paracelsus. And he used to attempt to cure people with antimony because it was known that antimony could purify gold very well. And he reasoned that if antimony can purify gold, then it can also purify people. Regrettably, most of his patients died. Now I will pour some antimony there, and as you can see, as I pour it into the chlorine, there is sparking going on because the antimony is combining directly with the chlorine to make antimony trichloride. Another example of a synthesis reaction. The next reaction which we have to demonstrate is the reaction between ammonia and chlorine. Now, ammonia is a very strong alkali when it's dissolved in water, that is. Normally it occurs in the form of a gas, but when it's dissolved in water, it forms an alkaline solution which has an extremely powerful smell. And as we have noted already, chlorine forms an acidic gas, and you probably know that acid plus alkali makes a salt plus water. We don't exactly have this type of reaction here. Nevertheless, quite a vigorous reaction does take place. If I can, Grant, could you remove the lid for me? As I pour the ammonia in, take it right off. There you notice a violent reaction taking place, and the white smoke which you see is a smoke which is due to, oof, dear me, as I said, ammonia is very, very unpleasant. I've just had a small breath of it. Nevertheless, we shall continue. The dense white smoke which is formed here is a smoke of ammonium chloride, which fortunately is relatively harmless. So there we had another example of combining two very poisonous substances to make one which is relatively harmless. Now, for the final demonstration in this series, the final demonstration in the series with gas jars, should I say, I'm going to demonstrate the reaction between hot turpentine and chlorine. Now, turpentine has a very pleasant smell, but you shouldn't smell it because it's very bad for you. It's also extremely inflammable. And I'm going to heat up a small quantity of turpentine. Actually, that's rather a large quantity I've got in there. Let's just pour some back in. There we are. A small quantity of turpentine shall be heated to boiling point in a Bunsen burner flame, and then I shall pour it onto a wad of glass wool which will be placed into the top of this cylinder, and we shall observe what shall happen. Now, you might be surprised to see that I'm heating a substance which is highly inflammable in a test tube, and indeed this is an extremely dangerous thing to do. However, the main thing here is to prevent the mouth of the tube from coming anywhere near the flame. Provided that we keep the mouth of the tube well away from the flame, there is no danger whatsoever that the liquid will catch fire. And are we ready now, Bernie? We're now nearly ready to go. Bernie's just going to, right, no, not yet. Now what's going to happen? I'm going to get this boiling. You're going to put the glass wool in, push it down, and I shall then pour some hot turpentine on, and we shall see what will happen. Are you ready then? Ready, go. Okay? We will observe a reaction there. The turpentine catches flame, catches fire spontaneously, and dense white fumes here are produced. There is some ammonium chloride being formed, and also, my word, a very smelly experiment indeed. Let's just extinguish those fumes. They're a little unpleasant. We'll pour some ammonia in. As I told you before, this neutralizes the very unpleasant effects of both the ammonia and the chlorine. Can you see the black smoke here, the black deposits on the side of the jar? This is due to the formation of carbon. Turpentine contains a very high percentage of carbon, and this is liberated by the reaction between turpentine and chlorine. For our final experiment with chlorine, I'm going to demonstrate the reaction between hydrogen and chlorine, two gases in fact. For this purpose, we are going to move over to a fume cupboard because of the extreme unpleasantness of filling a bottle with a mixture of hydrogen and chlorine. We shall now move over to a fume cupboard where we shall rapidly fill this bottle with a mixture, a 50-50 mixture of hydrogen and chlorine. Bernie, could you go past me and go over to the other side and turn on the generator? Turn on the generator. Now then, I have here a plastic bottle which was once used for Robinson's barley water. You'll know why it was plastic why I used a plastic bottle and not a glass one after you've seen this experiment. We're going to half fill this bottle with chlorine. Here it goes. I hope that's a reasonably pure sample we're getting. It looks a little smoky. Nevertheless, keep it going, Bernie. There you can see green fumes are already filling the cylinder. Rapidly, the bottle rapidly, should I say. Green fumes are filling the bottle rapidly. And I'm shortly going to, okay, turn it off now, Bernie, turn it off. Right, we shall now fill it with hydrogen. Can you move this, turn it on very, very gently. Turn it on, that's a little too vicious there. Turn it just a little too vigorous still, Grant. I know you get very excited with these gas cylinders and things. There we are. A tiny bit more. Yes, just a little too much again. There we are. Filling it up slowly. Good. Now then, that's fine. Can you now pass me the stopper for the bottle? Should they be? Oh, sorry. No. We want the. There should be a screw cap there. Can you have a look? Is there one lying there or
Yes,
not?
there is. In my pocket.
Is that it's in your pocket? Ah, here's another good. I do apologise once again. He had it in his pocket all the time, yes. Now then, we have here then a mixture of hydrogen and chlorine. Now this mixture is quite stable and unreactive when it's in a reasonably dark room. However, when we place it in the vicinity of strong ultraviolet light, the hydrogen and chlorine combine together explosively to form the gas hydrogen chloride. Now, could I ask you two chaps, at this moment, to move all the apparatus further away? I will deal with the real experiment here. No, just move this way, just this lot here, nothing else. What I'm doing here is I'm pouring some flash powder, which consists of magnesium and potassium chlorate, onto an asbestos mat, and I'm going to set it off with a special delayed action fuse powder, which consists of potassium permanganate and glycerine. Now the whole thing has to be done rather rapidly because it's been known for hydrogen and chlorine to react with explosive violence. Now can we quickly remove all of these bottles? Quicker, yes? All the bottles, pass them down, otherwise there might be a dangerous explosion resulting. There we are. That's right, move these jars away. Now, in this reaction, we are going to observe the chain reaction between hydrogen and chlorine, which goes off with extreme violence, which is set off by a bright flash of ultraviolet light, which will be generated by the flash powder which I have produced. A couple of drops of water help to catalyze the reaction, and we can stand back and watch. Just before as my final word, before we go into space with the explosion, can I just make one word of advice? On no account should you ever attempt experiments of this nature unaccompanied by qualified adults or in a laboratory by yourselves. These experiments can be extremely dangerous if they are done in the absence of qualified supervision. The fuse powder is now beginning to warm up, and we shall shortly observe an extremely bright flash, and it will be immediately followed by a very loud bang indeed.